Last Thursday, I think, I handed you these lab sheets. It says testing Bronsted Lowry acid-base reaction predictions. So instructions, number 1, use the 5-step method to predict the acid-base reaction. So you have sodium acetate, which is an ionic compound, right? Which means you don't actually have sodium acetate in your solution. You have sodium ions and acetate ions, right? One of those might be a base, one of those might be an acid or whatever. It's being mixed with hydrochloric acid. Now, I have a question for you. Does hydrochloric acid actually exist in water? No, it doesn't. When I say hydrochloric acid, immediately another entity has to come into your mind. It has to pop into your mind, okay? So hydrochloric acid does not exist. That means it's turning into another kind of strong acid, right? The strongest acid that can exist in water. Anyways, whatever. So what's going to happen? In this lab, you're going to need some things, okay? You need distilled water. So have a bottle of distilled water and just fill it up or whatever, right? Have your little distilled water squirt bottle thing. And then fill it up with distilled water. Does anybody need a reminder where the distilled water is in the lab? Okay, that's fine. So distilled water you need. You also need a spot plate or a drop plate. Is that okay? That's because anytime you're adding a liquid to a liquid, you don't need tons of them, okay? You don't need to fill an entire beaker full of liquid. So you just add a little bit of one liquid and a little bit of another liquid into one of these wells, and then try and observe what's happening, right? So you should get a very specific smell, and you might be able to recognize this smell because some of you use it on like a semi-regular basis, okay? The last thing you're gonna need is you're gonna need like a small beaker. I don't really care how small it is, but you need a small beaker. For all of the last 4 labs on here, for all the last 4 tests that we want you to do, a small beaker, with a stir stick would be nice. Okay, so let's go through really quickly what we're going to do. In the first test, there's a spot out there at the lab bench that's named station number 1. Okay, it's station number 1. And so when you look at station number 1, okay, you need sodium acetate solution and hydrochloric acid. You put a little bit of the first one, a little bit of the second one, and try and smell it. See what happens. For the second one, second station, sodium benzoate solution is mixed with sodium hydrogen sulfate solution. You should see something that is insoluble. Now, I'll give you a hint, okay? Benzoic acid, C6H5COOH, should be a solid in water. Benzoic acid has very low solubility in water. So this thing should have low solubility. So if you predicted that this thing would be made, then you should also predict that there would be a precipitate, okay? Again, you're just going to do station number 2, right? You're adding 2 liquids, so you just need a spot plate, that's all. Station number 3, and every other station, you should just do in a small beaker. And you'll rinse it out every time, and then you'll dry it out, and then you'll reuse it every time, right? Solid sodium chloride, otherwise known as salt, is mixed with water. Observe the pH. Now what that means is once you've mixed the 2 together, take a strip of pH paper, put it in, and see what kind of pH it is, right? Now, under normal circumstances, like a grade 9 student or whatever, would a person who wasn't in Chem 30, would they be able to tell you what kind of a pH salt mixed with water would be? Maybe, right? When you mix salt with water, are you really, really concerned about getting a chemical burn on your hand because of that? Probably not, right? Okay? So in your prediction, you should predict that, you know, you're going to make something neutral, or at least a neutral mixture, right? Okay. Okay, here's where I want to be very careful. The next two, aluminium sulfate and iron 3 sulfate. You're using a beaker, okay? So you're going to take your water. You don't have to use the spray part of it every time. You just put a little bit of water in here and add a little small amount of the iron 3 sulfate or the aluminium sulfate, and then you're going to test the pH, right? If you predicted that you would make hydronium, let's just I have no idea, okay? But let's say you predicted you would make hydronium. What do you expect to happen to the pH of this solution? Would it be higher than 7 or lower than 7? Lower than 7. Lots of hydronium means acidic. Acidic is less than 7, right? Okay. So let's see. I want to be very clear. You're going to get weird results at 4 and 5. You're going to get weird results. Whatever. Just as long as you understand, you're going to get like the opposite results that you're predicting. Okay? And we'll talk about why that is later. Station 6. Add solid sodium hydrogen carbonate is added to sodium hydroxide solution. There's instructions on the card for station 6 out there. There's very specific instructions out there, and it's I don't know, whatever, it doesn't matter. It's just very specific. So do those, follow those instructions. Then the last one is just have your small bottle of water, right? Add 2 to 3 drops of phenol red or bromothymol blue, doesn't matter, whatever, blah. Okay, and then what do you have to do? You have to slowly exhale into the water. You know what I mean? So just do that, and do that for a long time, and see what happens to your beaker. It already started doing something. Anyways, whatever. So I'm not marking question number 7. I'm not marking question number 7 because I want to go through that with you when we come back from the lab. Is that okay? Okay. Because the aluminum sulfate and because the iron 3 sulfate are actually quite dangerous, I want to be very clear. If you get any on your hands, immediately rinse them off with water and wash them with water. You need aprons, like honest to goodness this time, because if you get that powder on your clothes and then you spill water on your clothes, they become actually very corrosive. Okay? So you're going to wear an apron. You don't often do this, but you are going to wear an apron today, and you are going to wear glasses, and you're going to have the glasses on your eyes, not on your forehead the entire time. Are we good? Yes? Okay. I accidentally... Okay, we're going to take like another minute to kind of just finish up what you're doing, and when the other people get back into the class, we'll talk about the expectations for this. We're also going to go through a couple examples together because I think we're still kind of not on the same page. So I just want to make sure that we truly understand what I'm asking us to do here. Okay, can we all, like, somebody pick a number 1 through 6.
5.
Well, let's take 5. Okay, for right now, let's just take 5. Okay. So let's add some iron. Yeah, that's what I have here, so that's good. Let's add some iron-3 sulfate to water, and let's see what's going to happen. First thing I want us to do is I want us to predict what kind of a solution we're going to get. And so, okay, that should be fine. You've got solid iron-3 sulfate, but you're adding it to water. So let's see if it's going to dissolve, right? Let's figure it out. Chem 20 data booklet, Chem 30 data booklet. And iron-3 sulfate is an ionic compound. So let's see. I'm going to look under sulfate. And do you see iron-3 down here? No. So like that thing will mostly be soluble. Whatever the mixture will mostly be soluble. So the iron-3 sulfate will dissociate. It will split up. Okay, all right, no problem. So instead of having iron-3 sulfate, we've got iron-3 plus aqueous. We've got sulfate, 2 minus aqueous. And we're adding this to water, so we've got water, liquid. Perfect. Now, is iron-3 plus an acid, a base? Is it nothing? Nothing. According to our chart, it's nothing. So I'm not going to put anything. Is sulfate, can sulfate act as an acid, a base, or nothing? It can act as a base, right? So our sulfate can act as a base, and then water, can that act as an acid, a base, or nothing? Acid and base, right? So it can act as an acid and, and a base. Perfect. So let's take a look at our data booklet. And we're going to go through here and we're going to try and find the strongest acid and the strongest base. When I look through my acids, I only listed 1 acid. Would you agree? Sorry, I listed 2 acids. No, 1 acid. 1 acid. I only listed 1 acid. So nothing, water. Would you agree water's our strongest acid here? Okay, perfect. So water is our strongest acid. And then we look for our base. And, okay, I'm looking for sulfate or water. Nothing. Sulfate or water. Oh, I see sulfate and I see water. Yep. Which one of these is the stronger base? Sulfate. Okay, all right, perfect. Sulfate. So our sulfate is our strongest base. So you're right, one reacting with the other. So water reacts with sulfate. And it should produce hydrogen sulfate and hydroxide. Now, the resulting solution, let's think about this. If you added these 2 things together and you made this, what kind of a pH would this mixture give you? A high pH or a low pH? It should give you a high pH. Why? The hydroxide. Would you agree? If something's making hydroxide, that sounds like a base to me, right? So this solution should be basic. So let's test this, and let's see if it actually happens, right? So I'm going to put a little bit of water in here, and I'm going to test. I'm going to add some of this. And I should be doing this a little bit more carefully than what I'm doing, but c'est la vie, whatever. Okay, perfect. And I'll use my absolute technical instrument, a pencil, to be able to stir it up. And instead of instead of pH paper, I'm going to use bromothymol blue because bromothymol blue is blue in basic solutions, it's green in neutral solutions, and it's yellow in acidic solutions. So what color should the bromothymol blue be if this is going to be basic? It should be blue, okay? So I'm going to add my bromothymol blue to this thing, and what color is it? It's yellow. There's something wrong with our definition of an acid still. Do you know how we redefined acids? We've redefined it a couple times. We used to say acids are something that has a proton, or it makes hydrogen ions. And then we said, okay, that doesn't work. Acids are something that makes hydronium in solution. And then we were like, oh, okay, well that doesn't work. And now we're saying acids, the Bronsted Lowry theory of acids, is acids donate a proton. Does iron 3 plus have any protons to donate? It is an acid, and it's actually a very corrosive acid. Iron 3 plus ions are actually a really corrosive acid. Man, I keep forgetting to bring the money. They're selling cookies and they're so delicious. Hi. Sorry, I don't have any money. But yeah, thank you. Yeah, thank you. Shucks, noodles. All right. So this, the reason why 4 and 5 are on here, aluminum ions and iron 3 plus ions, they're a different definition of an acid. There's something called a Lewis acid, and you will deal with Lewis acids if or when you get to university and you start studying general chemistry at a university level. Lewis acids, if a traditional acid is a proton donor, a Lewis acid is an electron acceptor. It's a very weird definition of an acid, but it's just as long as you understand that whatever, that's totally fine. Okay? So obviously, the evidence was, the pH was less than 7. And the analysis, does the evidence match with what we predicted? Should this mixture here have a pH less than 7? No, it shouldn't. So our analysis is our prediction was not observed. Do you know what I mean? There's something wrong with our definition of an acid. Now, the Bronsted Lowry theory of an acid is still good. It still works in 90% of the time, okay? But it's not the best. It's not good enough. Now, out of this whole question, we wrote down a buttload of stuff. What would be, did I say what the only thing I was actually marking was? The reaction. This is the only thing that I care about right now, okay? So out of all of these things, this is the only thing I care about, okay? Let's do really quickly number 7, because that's the other one. Can I erase this? Is that okay? Yeah. But does this process make sense? That's really all I care about, this process, John. Oh, yes. Thank you so much. I really appreciate you letting me know. Hey, this should be reactants favored, right? Because this is big time uphill. This is like majorly uphill, right? So you could put reactants favored or less than 50%, whatever. But yes, I would like you to do that. Okay, I'm going to go ahead and erase this. And we're going to talk about number 7, because I said that we were going to talk about number 7, because I haven't taught you really how to do it yet. Okay, the instructions said add 2 to 3 drops of phenol red or bromothymol blue, whatever, that's totally fine. I didn't add 2 to 3 drops, I added a buttload, okay? Now, what did I say? Bromothymol blue is blue in what kind of mixtures? In basic mixtures. This is actually a basic solution right now. This whole thing here, this is not neutral, it's basic, okay? And the reason why it's basic is because this indicator, bromothymol blue, starts to degrade, it starts to break down and react if it's in an acidic solution. So we keep it in a basic mixture to make it last a really long time, okay? So when I add a basic solution to water, what am I slowly turning the water into? A basic solution. Does that make sense? The more bromothymol blue I add to this thing, the more basic it becomes. Does that kind of make sense? Okay. So this is now no longer water. It's water and bromothymol blue and the base that we use to keep the bromothymol blue. Now, we're starting with blue, so that means this must be basic. What am I supposed to do? Using a straw, slowly exhale into the water. That's insane! What's going on? What did I say? What did I say bromothymol blue was in a neutral solution? Green. Is that kind of green? Yeah. Yes, okay. And if I kept going, what's going to happen?
Getting light.
Is it getting more and more yellow? It should be. No, whatever. Okay. But we observed a color change. Now, the first thing I want to do, what are the only things I'm really adding here? I had water, I had bromothymol blue, whatever. I had water, and what am I doing to it? I'm adding carbon dioxide. Let's look in our data booklet, and I want you to look, don't look under the acids, don't look under the bases, but look under the names. Is there an acid? Look under the names of everything. Is there an acid that represents the mixture of carbon dioxide and water? What is its name? Carbonic acid. Otherwise known as the bubbly stuff that makes soft drinks soft. You know what I mean? Right? If you go to a restaurant and you order, I don't know, Diet Pepsi or whatever, right? It should have lots of carbon dioxide in it. That's what makes it bubbly and for the most part, tastes good, right? That and sugar, a buttload of sugar. So when I add carbon dioxide and water, I get carbonic acid. That's what I'm doing. I'm making carbonic acid by blowing my breath through this solution. So again, I'm not marking this. But the production of carbonic acid is just CO2 plus H2O is in equilibrium with H2CO3, aqueous. Pardon? Less than 50%. This is a big time reactance favor. Now, the reason why you should probably know that is because what happens when you open up a can of pop, or what happens when if you shake the crap out of a can of pop and you open it up, what's going to happen? Right? Okay? So that means this is big time reactance favored. If you have a buttload of carbonic acid and you open the system, we need a closed system to maintain equilibrium. So if you open the system, the carbon dioxide leaves, and this big time shifts over to the left. Okay? Now, I'm adding carbonic acid, and let's look at bromothymol blue. Let's look at bromothymol blue on your data booklet. 1, 2, 3. There we go. So we're looking at our acids, table of acids and bases. And do you see bromothymol blue on here? Yep. Yeah, bromothymol blue. It has, please, I want to be very clear. Every indicator has a 2-letter code, okay? Bromothymol blue's 2-letter code is BB. Can you understand why bromothymol blue's 2-letter code is BB? Now, there is no element BB, right? When you look at the periodic table, BB doesn't exist. So this is, they're trying their best to pick two-letter codes that don't exist. Now, if you were to look at trinitrobenzene, its two-letter code is NB, and there is an element NB. Right? Pretty sure? Niobium. So they're trying their best to pick two-letter codes that make sense, and sometimes they conflict with other things. Okay. Okay. Now, what color was our bromothymol blue in basic solutions? Blue. Okay. So it's blue. So yellow's on the left, blue's on the right. So which form is our bromothymol blue mostly in right now? Is it HBB or is it BB minus?
BB minus.
Yeah, it's BB minus. This stuff is BB minus, okay? When I add carbonic acid by blowing into the solution, when I add carbonic acid, the acid reacts with the base version of the BB minus, okay? So what we get is we get H2CO3. Is this a weak acid or a strong acid? It's a weak acid, so it's not going to break up. H2CO3 aqueous. It could react with water, or it could react with BB minus. Now this is complicated, but I need you to listen up and I need you to pay attention. H2CO3 is an acid. Water could be an acid, it could be a base, and BB minus could be a base. Which one of these acids is our strongest acid present? Is water a stronger acid, or is carbonic acid a stronger acid? Carbonic acid is a stronger acid. You can just look at your data booklet, you'll see that, okay? Now, what's a stronger base? Is water a stronger base, or is BB minus a stronger base? Keep in mind, they're on two different pages. Take 30 seconds, try and figure out which one is a stronger base. Is BB minus, is that a stronger base? Yeah. Then, it's water. And water is a stronger base. If we were to take this thing, and we were to plug it into this state, where would it go? So where would 5 times 10 to the 3?
We can watch this.
Does that make sense? Right? 'Cause it's better. Yeah, but they give you a number, they give you a Ka to be able to, so you can sort it, right? Yeah. Okay. This is complicated. I need you to kind of pay attention, okay? What does your gut tell you? Is BB minus a stronger base, or is water a stronger base?
BB minus.
Okay. So let's prove that to ourselves. What would be a stronger base? Okay, I gotta keep going back, okay? What would be a stronger base? Water or something below water in the base column? Something below water, right? Okay. So let's figure out, is BB minus, is bromothymol blue, does that row fit below water or above water? What are the Ka's of everything above water?
Very large.
Very large. What are the Ka's of some of the things below water? Well, it depends, right? Something directly below water is 10 to the negative 2. Something way below water is 10 to the negative 13. Let's figure out where bromothymol blue will fit. What is the Ka? Look up the Ka for bromothymol blue. Flip the page over. It's 5.0 times 10 to the negative 8, right? Yeah. So 5.0 times 10 to the negative 8 means it would be here. So that BB minus is right here. BB minus is right there. Is it a stronger base or is water a stronger base? BB minus. Does that make sense? Acid-base indicators are acids and bases. They are chemicals that are physically acids and bases themselves. Okay? If I took this bromothymol blue, if I took the base version of it and I started rubbing my hands together, I could give myself chemical burns because it's a weak base. Okay? It's a relatively strong weak base. So what we can do is we can take a look. Okay, this is our strongest base. So this thing and this thing are going to react together, right? So we're going to get H2CO3 aqueous reacts with BB minus aqueous. And it's going to create, right, the acid transfers a proton to the base. So it's going to make HCO3 1 minus plus HBB aqueous. What's the color of BB minus? Blue. What's the color of HBB? Let's take a look. It should be yellow, right? When I look at HBB, it's yellow, right? So this thing is yellow. How can I get this equilibrium to shift towards the products? I can add more carbonic acid. Does that make sense? When I add more carbonic acid, when I blow into this straw, I'm shifting the equilibrium from the blue version into the yellow version. Are we okay with that? That's a complicated question. That's why I'm not marking it, because that's so complicated and nobody would have ever figured that out. Okay? But that's totally fine. There are 5 other reactions, and I'm realizing right now probably a lot of people aren't going to get them done by the end of class. So you got to hand them in tomorrow at the beginning of class. If you want to hand them in today, feel free to, but it's going to be due at the beginning of class, right when you walk in tomorrow. So you see which ones have those. If I were to look at those.